Hello class, this is the walkthrough for our third Ansys project. We are going to be looking at what's called a Rayliegh system. And just so that you know where we're going, let's go ahead and take a look at the animation that should be produced at the end of the simulation. So this is the initial state. We have a system or cell which has periodic boundary conditions, which means what passes through our right boundary will come in through our left boundary. That'll become apparent in a moment. In this project, we're going to be using the heat transfer governing equation as well. So we're going to be using the energy equation. We'll talk about that in the setup. And so what's going on is we're heating a system filled with air, where we're heating on the bottom and cooling on the top. And so because the fluid at the bottom of the domain is heated, the density actually decreases. Whereas the fluid at the top of the domain is cooled, there the density increases. And so now you have this instability where you have higher density fluid at the top, lower density fluid at the bottom, and because we've turned gravity on in this system, you're going to create what are called convection cells. So the hot air will rise, the cool air will fall, and we'll sort of get these overturnings because we're constantly cooling at the top and heating at the bottom. So let's go ahead and take a look at this. So in the initial portion of the simulation, we can go ahead and stop here. So the initial portion of the simulation, we can see that the boundary layer of the temperature increases, but eventually we see some instabilities occur where we get sort of these patches of high density fluid falling in what's called a plume. So this is sort of a small narrow filament that falls from the top boundary to the bottom boundary. Eventually more and more of these filaments start to grow, and these instabilities grow over time, causing the system to destabilize and eventually forming large overturning patterns. And so this is the temperature field. We can take a look at the velocity field. The initial times, the velocities are very small, and so it's not until the overturning really starts kicking in that we get to start seeing some higher velocity signatures. So this is now a high velocity signature as we're seeing many of these convection cells being developed. And then eventually many convection cells start merging to form just larger convection cells and fewer of them. Okay, so we're going to go ahead and walk through the process of getting to this point of having a nice convection cell simulation. All right, we can close this, and we will go ahead and close our simulation as well. So let's go ahead and save this just for reference. So as we walk through the simulation, I'm going to go ahead and write down some of the key parameters and then post that for you so you have that available to you as you're walking through. So as you notice, we're going to start with a very simple geometry. It's just simply a rectangle. We're going to create that geometry first, go through the meshing process, and then ultimately where we'll probably spend the most time is talking about the setup and solver. But for now, let's go ahead and restart our workbench so that we're starting from scratch. Okay, so we're starting from a clean workbench. We're going to just go ahead and run our Fluent. Pops it up. For our geometry, the properties, we're going to make sure we're running a two-dimensional simulation. There are convection cell simulations that do look at 3D. Those are obviously more expensive but are much more accurate. Our focus is just going to be on a 2D implementation of this type of geometry. Okay, so we've got our 2D properties set. We're going to go ahead and use Design Modeler again. And so the properties that we're going to be using for our geometries, we're going to create a rectangle with one corner on the origin. The rectangle will have a height of 0.02 meters. And a width of 0.2 meters. Okay. So going into our design modeler, we go ahead and click on the z-axis because we want to plot our sketch in the xy plane. Click on the xy plane so we can see it. Click on sketching to start creating our rectangle. we'll just do the 2 points, so we pick our bottom corner to be here at our origin. You see, get the p-value, so it's at the point, and just create a rectangle. Now we're going to set our dimensions, so we click Dimensions. General is fine for the 2 types of dimensions we want, so we're going to set 1 as our height, and 1 as our first vertical dimension, so that's our height, so that's going to be our 0.02 meters, so that's going to be very short relative to what we drew. And then our width, our horizontal distance, is going to be 0.2 meters. Okay. We can resize. You can still see our geometry is quite small, so we're going to move our dimensions a little bit closer to the geometry, just so that we have the ability to zoom. Okay, so now we can zoom again, and we see our rectangle. Okay. So I know for previous projects we've done the naming of boundaries here, but we're going to go ahead and just reserve that for the mesh. It's the last thing we'll do in the mesh before we jump into our solver. So at this point, we'll go ahead and done, so we can save our project. And again, all this is being done in our VMware system. We'll call this, we'll do our walkthrough number 2, since this is my second time to go through it. Alright, so we've done that. We can close our design modeler since we're done with this. And move on to our mesh. So for our mesh, we're going to just use a simple quadrilateral mesh where we're using face meshing to create those cells. We're going to just have a uniform cell size in the horizontal and vertical directions. So this is pretty similar to what we did for our first project where we were looking at floating. So we'll load up, the mesh solver should be loading up our geometry. We got some errors. Let's take a look at what our errors are. Okay, so our error, what we forgot to do is we created our sketch, but we actually didn't create a bottom. So let's go back into our geometry. Starting up the design modeler again. And so you can notice we have zero parts and 0 bodies, which is obviously a problem. We do still have our sketch though, so that's good. And we can do the final step, which was skipped, which is to create a surface from sketch. Sketch is selected. Creating the body, all set, and we can generate, and there's our body. Okay, so now we can save and move on to our mesh. Okay, so we can refresh our mesh. Hopefully we won't get any errors this time. Okay, so it looks good, and we can go ahead and edit our mesh. We had no reopen, that's fine. Okay, so now our geometry is in there. We can just take a look at what our default mesh is. So, sort of similar to what we're looking for, but obviously at a much lower resolution. So let's go ahead and talk about the properties of our mesh. Put in geometry, create surface, new sketch. So you guys remember to do it since I forgot. Okay, so for our mesh, let's talk about the properties. So we're going to, for the top and bottom, we're going to have 400 uniform divisions. For the left and right, we're going to have 50 uniform divisions. And then after we've created those sizings, we're going to go ahead and use face meshing to create quadrilaterals. Okay, so let's go through that process. So top and bottom, so we're going to select sizing, we're going to select some edges, we're going to just make this full screen. So we're going to just scroll through the top and bottom. So those are our two geometry aspects. We're going to set the number of divisions to 400. Okay. Looks good. We can generate our mesh again if we want, just to see the higher resolution at the top of our domain. Hard down here. Okay, so higher resolution obviously at the top and bottom. Now we're going to go ahead and go through and do our left and right. So left and then our right boundary are selected. We can apply it for those two faces. We're going to do, or two edges. We're going to do number of divisions and set that as 50. Update our mesh again. Okay, so you can see we have a combination of quadrilaterals here, some rectangles or triangles elsewhere. So we're going to make this uniform. We're going to use face meshing. We're going to select our surface, apply that to our geometry. So for our entire face, our method is going to be quadrilateral, so that's fine. And then we can take the final step, which is apply our face meshing. Okay, so it looks good. Next thing we're going to do in our mesh is we're going to name our boundaries. And we're going to just simply use top, bottom, left, and right. Okay. So we can go back to selecting edges. We'll select the bottom edge, right click, create name selection, bottom, top edge, click, right click, create name selection, top. Click on the left edge, right click, create name selection, left. This is the right edge. And we should be able to see our name selections, bottom, top, left, right. So that's all we need to do for our meshing. So we can go ahead and save our project. Okay, we can close our mesh, update this just so we can get that done before we go into our setup. So now we have our domain, we've identified our boundaries and have our mesh, of course. So we can, once all that's updated appropriately, we can move into our setup. So for our setup, we're going to do a transient simulation where we are using the heat energy equation, which allows us to model the heat transfer occurring. That's heating up the air. For our VMware simulation, we're going to do a couple of things in the Fluent launcher. So assuming you're operating on VMware, you have a little bit more flexibility. If you're working on a personal computer, you may not have as many processors, but double precision, that's just the level of accuracy of your numbers. As we've discussed a little bit in class, there's a finite representation of each number. Using double precision basically allows us to have more accurate representations of those numbers. But what's really important is we're going to increase our number of solvers, and on VMware you can use up to 4 solvers. And that's going to just speed up our calculation just a little bit. Okay. So Fluent will be starting up. So we'll just add those things to our setup. So you can use double precision, and on VMware machines, you can use 4 processors. Okay. And part is open. There we go. Okay. So we have our domain loaded, which looks great. We have our general properties that we can set for our simulation. We are going to simply use the pressure-based. I think that's sufficient for our simulation we're doing. Absolute planar. We are going to be doing a transient simulation, and we are going to turn on gravity. So we're going to set gravity as minus 9.81. So we're obviously doing everything in meters per second in the y direction. So let's add those things to our list. So we're going to use a transient solver. Set gravity to y equals minus 9.1. Okay. Then in models, we're going to select a couple models. So by default, our energy equation is off, so we need to turn that on. That allows us to have the temperature variation. And then the other one is the viscous simulation. We're going to, instead of using the k omega equation, we're going to be using k epsilon, because that in particular allows us to do an enhanced wall treatment, which is necessary for some of our simulations. Okay, so k epsilon enhanced wall treatment. And the energy equation should be turned on. Okay. Next is going to be our materials. We're going to be using air with the slight modification that we're going to change the density to incompressible ideal gas. And so as the temperature changes, that's going to directly impact the density. Okay, so materials, fluid, air is preloaded, so we can just simply edit our air. Density, you can see, is initially set as a constant value. We have a couple options here. The one we're going to be using is incompressible ideal gas. For the homework, you are going to be varying this thermal conductivity a little bit, but for now, the default is 0.0242. Okay, we're going to create change and close. Okay, so we're done with models and materials. You can go ahead and confirm that the working fluid in your domain is air. Shouldn't be anything else because we haven't loaded anything else, so that's good. And now we're on to the boundary conditions. So you can see our 4 named boundaries have all been by default identified as wall boundaries. And so let's discuss which boundary conditions we're going to use. So for the top boundary, we have 2 different types of boundary conditions that we have to implement. One, we have to implement a fluid boundary condition, so slip, no slip, inlet, outlet, those kinds of things. And then we have to implement a temperature boundary condition because we've added the heat equation. So for the top, we're going to be doing a free slip with a constant temperature of 300 Kelvin. Bottom is going to be also free slip with a constant temperature of 2000, so quite one. And then we're going to make our left and right boundary conditions periodic. Okay, and we'll walk through how to do that. So top boundary first. So to make the top boundary a free slip boundary condition, we're going to specify shear and leave these values as 0. Then to set the temperature condition, we're going to click on our thermal tab, set our temperature, and leave the temperature at 300 Kelvin for the top boundary condition, so that's all set. Okay. For the bottom boundary condition, we're also going to set this as free slip, so specified shear. Both these values should be 0. our thermal. We're going to set our temperature to 2000. Okay. So next is our left and right boundary conditions, which we want to use a periodic boundary condition. This is a little bit more complicated to implement, and so what we end up having to do is perform this operation in the console. So in the console, go ahead and hit Enter, and you should see a little arrow pop up, and there are some folders with different operations available to you. So we're going to type in the following. We're going to type in mesh / modify zones / make periodic. Okay? So in here, mesh / modify zones / make periodic. So this is going to cause the console to go through the operation of making our left and right boundaries periodic. Okay? So we're going to go ahead and hit Enter. It's going to bring up some options for us to input some values. So periodic zone. So what you'll notice is next to our boundary conditions, each boundary has an ID number. So the bottom boundary has an ID number of 5, top has an ID boundary number of 6, and so we're going to make our left and right boundaries, ID numbers 7 and 8, the periodic boundaries. So that's the case for mine. Depending on the ordering of your simulation, you may have different values. So this is something that you have to be cognizant of, is take a look at what is the ID value and make sure those are the two values you're plugging in here. So mine are 7 for the left and 8 for the right. So I'm going to type in 7, and my shadow zone is 8. Is there any rotation required for the periodicity? No. Both of the values are, or both of the boundaries are vertical, so I can type in no. Create periodic zones, yes. Auto detect translation vector, yes. So these are things that Ansys can do in the background and figure things out. Pretty straightforward since our domain's really pretty easy. Okay, and so what you'll notice is that your boundary condition has changed to be a periodic boundary condition, and it states only that the left is there. So the right boundary condition, that second value that we put in, that shadow boundary, no longer is available to us, but that's fine. Okay, so we're done with our boundary conditions. Now we can go ahead into the solution. And so we can type that in there. Mesh, modify zones. So for our solver, we're going to do a couple new modifications. We're going to actually define a couple properties that we're going to analyze or observe during the course of the simulation. In particular, you're going to be doing this for your homework. So we're interested in, we've set these top and bottom boundaries as constant temperature values. So the question is, how much heat transfer is required to maintain those constant temperatures? So we're going to create two definitions. So report definitions. So we can see we've got a couple baseline ones. Flow time, that's the time in the current time step. Delta time, that's the time step size. Iterations per time step, so that tells you how many iterations were necessary to get convergence or to perform each time step. So we're going to go ahead and create new. And in particular, we're going to do some flux reports. So we're going to look at some heat transfer rates. So we're going to create a new definition. We're going to refer to this as report def. And we'll call this bottom flux. And so we can select our bottom boundary and select the type of flux that we're looking at. So we have mass flux if we were interested in that, but we're primarily interested in the heat transfer flux. And we're going to get the value output over for each time step, which is fine. Okay? So now we can see our new measurement is here. We can repeat this with another flux measurement, heat transfer rate through our top boundary, and we'll call this top flux. Okay? So we created our new definitions, which we'll use in a moment. For our monitors, we're going to define our residuals. We're going to use 10 to the minus 4. So it's going to be 0, 0, 0. We are going to leave the energy of the higher resolution or a residual of 10 to the minus 6. And everything else will be 10 to the minus 4. So that's all good. Now what you'll notice is a report file. So this is where you can actually output those values or those quantities that are being evaluated for each time step. So report files, we're going to create a new file. And we're going to report file flux. So in addition to our flow time, we're going to output both the bottom flux and the top flux. We're going to save this in the file, heat, transfer, and we're going to call this a txt file. Okay? We're going to get data every time step. Okay? All right. So once the simulation starts, at the conclusion of each time step, it's going to perform those calculations of the heat transfer at the bottom and the top of our domain, and then copy those values into that text file that we just generated. We're needing to keep track of the solver steps. So for solver, so report definitions, we needed to create the top and bottom flux calculation. We went ahead and set our residuals all to 10 to the minus 4, except our energy, which is 10 to the minus 6. We created a report. That outputs the flux calculation. Okay. Now we're going to initialize. We're going to use a standard initialization where we're going to set the temperature as the average of the two temperatures in our boundary. So we have 300 and 2000, so that would be 2300. So our average temperature is going to be 1150. We're going to initialize. Now we're going to go ahead and create some of our graphics. So first we're going to create a contour. This contour is going to contain our static temperature. We're going to call it contour temp. That looks good. So let's go ahead and save and display. Temperature is updated. Everywhere the temperature is 1150. Okay, so that looks fine. We're going to go ahead and create a vector field. And in this case, we're going to plot our velocity field, and we're going to go ahead and not auto scale so that you guys can hopefully see the velocity field developed a little bit better. Velocity magnitude is fine. We're going to skip a couple of the vectors so that they show up a little bit bigger. So we're going to skip maybe every 10th vector. Sorry, not auto scale. We want to do auto range. But we're going to set our minimum value to 0 and our maximum value to 1 meter per second. Okay. So let's go ahead and save and display here. We don't see anything. The boundary doesn't show up, which is not ideal, but okay. So hopefully velocity vectors will start appearing. And we're going to go ahead and add, create a solution animation for both figures. Okay. So calculation activities, solution animation, create a new one. First one will be animation temp. We'll update the figure every time step and contour temp. Okay. And actually, why don't we go ahead and make sure we can actually see what the window is looking like. So let's just display this again. So again, for the solution animation, if you want to zoom in view, you have to do that manually. So we can zoom in a little bit here, and we can use the active view, and that'll be the figure that's produced for our animation. We're going to create another one with our velocity vectors, and we'll use the active view for that as well. Okay, so we created our solution animation. We've initialized the problem. The last thing we have to do is run our calculation. Okay. So for the runner calculation, I want to go ahead and make sure that we get nice resolved, converged results. But what we'll notice is that your ability to get resolved results changes over time. So we're actually not going to take too many steps, but we are going to allow a huge number of maximum iterations just so that you guys can get a feel for how the amount of steps or amount of iterations changes as the dynamics change. So we're going to go ahead and set the number of time steps to, we'll start with 30 for now. We're going to set the time step size to 0.05. The maximum number of iterations, so this is not what you have to do for your homework, but for just educational purposes, we're going to set this value to 1,000. So this is a huge number of iterations. And we're going to report pretty infrequently. We'll report every 50 steps. Okay? So let's just update that in our solver. So we have 30 time steps, 0.05 seconds per time step, 1,000 max iterations per time step, and then 50 iteration reporting interval. So I think that's all we need. Go ahead and run calculate. So once it starts, I'm going to go ahead and let it run. Obviously, you can zip forward in the solution if you don't want to see how long it runs, but it does give you a barometer of how long at least my VMware implementation is taking to perform. So the calculation has started now at roughly 32 minutes into the video, and we can see we have a huge number of these lines, and each one of these lines corresponds to a different equation that's being calculated. And so in particular, we have our continuity equation. Obviously, that's from our fluid, x and y momentum. Those are Navier-Stokes. But because, and then our energy equation comes from our heat transfer, these K and epsilon values are coming from the fact that we're using a turbulence model as opposed to just simply using the laminar viscous simulation. So a couple other things. We can see the number of iterations necessary for the first couple time steps was a little bit longer than what we're seeing here. And currently, if we look at our field, we're still in that stable regime. We haven't really developed any of the filaments occurring. Okay. So things are getting quicker and quicker. So again, we're skipping 50 iterations for the updates, which is fine. And so the number of iterations continues to decrease, but now as we start to take a look at the temperature, my guess is we're going to start seeing one of our filaments forming. So you can see a little bit of disturbance here. It's not too big yet, but now we can definitely see, okay, we've got some disturbances that are going to start amplifying. And so if we look at our scaled residuals, you're starting to notice that the number of iterations is increasing as that instability grows. Okay. Overall, though, I mean, we performed 2,500 time steps. It's been about a minute 45 or so, so it's moving along pretty quickly. Go back to our static temperature field, so now we can start really seeing the development of our convection cells. If we look at our velocity field, we can see sort of these are nice vortices. These are counter-rotating vortices that are being developed as our convection cells form. Okay, so the good thing is that so far, at least, we've reached convergence for every single time step, and we're using a pretty large time step for this type of system of 0.05. Okay. So the convection cells continue to grow, and you can sort of get a rough feel for like, okay, this is one convection cell, 2, 3, 4, 5, 6 or so. And what you'll notice is that as time progresses, this number of these convection cells, sort of the number of pairs of up and down, so up being the high temperatures moving up, the low temperatures moving down, the number of those pairs will decrease. So like this is an example where we're starting to see 2 convection cells merging. And my guess is that some of these other guys will start merging as well pretty soon. So again, taking a look back, we're getting roughly the same number of iterations now as required for each time step, so evaluating here. So it looks like it's about 300, 350 iterations to reach convergence to the criterion that we've set. So for the homework, we've set a maximum number of iterations of 100, which means for some of your time steps you may not reach convergence, which for just the homework exercise is okay, but obviously you want to be a little bit careful with how confident we are with the results for a simulation where you don't reach your convergence criteria. Okay, so looking back at the temperature, we've seen now we have far fewer ups and far fewer downs, so the number of convection cells has decreased as well. So I think we should be getting pretty close. So we only have a couple more time steps, and then we take a look at the video. And then finally looking at the output file. Okay, so we've finished up. We ended up taking 7,100 iterations to perform the 30 time steps. So that's something on the order of like 270 or so iterations per time step. But obviously in some cases it went faster, some cases it went slower. Let's just confirm. Let's take a look at our animations. Playback. So we'll go ahead and play our temperature video. So that's a little bit easier to see how we're getting the convergence of the convection cells. Let's go ahead and take a look at our velocity video. Okay, so then we get sort of some hot spots, high velocity profiles along the bottom, and some vertical velocity profiles showing up here as well. Okay. All right, so it looks like our simulation worked. We can go ahead and save this. And while this is saving, let's go ahead and look into where our text file is. So my files are stored in this RB walkthrough number 2. And so you can just do a search for our .txt file, which hopefully is there. So report file heat transfer, so that's the file that we were, that's the report file that we generated. We're going to want to open this, at least for now, we're going to open this with a notepad. It just allows us to see the values. Obviously, you can use the data conversion M file that was used in a couple homeworks ago. But basically what you're seeing is the time step, flow time, and then the fluxes through the bottom and the top, and these are the particular values. So through 30 iterations, our flow time was 1.5 seconds. And then you have your fluxes through the bottom, and then our flux out the top of the boundary. And so you can see they're not exactly matched, which means the convection cell is causing some fluctuation in the amount of heat that's coming into and out of the system. All right, so that concludes our walkthrough. We'll do some of this in class just to cover any questions you might have, and I'll post the PowerPoint through all of